Modern rockets are becoming so massive that older launch pads can no longer support them. Spaceports are evolving into gigantic industrial complexes. Some launch pads now cost billions of dollars to construct. The future of space travel may depend more on launch infrastructure than on rockets themselves. Every mega spaceport is a machine built from 5 tightly interlocked systems, each one essential to launching and relaunching the world's largest rockets. At the heart of the complex lies the cryogenic storage farm, vast tanks of liquid methane and oxygen kept at temperatures colder than Antarctica. These fuels can only be handled by vacuum-insulated pipes and active cooling loops, where even a minor leak or temperature rise risks hours of delay. Next comes the flame diverter, a reinforced trench or steel plate that channels exhaust hotter than molten lava away from the pad. Its design must survive thousands of degrees and the equivalent of a small earthquake every time engines ignite. Above the trench, the water deluge system stands ready to flood the launch mount with hundreds of thousands of gallons in under a minute. This torrent absorbs the deafening acoustic shock, sound pressure that can shatter concrete and rattle windows miles away. The mount itself, a steel or concrete structure taller than a city bus, must anchor the rocket through liftoff, absorbing forces measured in millions of newtons, then reset for the next launch in hours, not weeks. Finally, the logistics chain ties it all together, including rail spurs, heavy lift cranes, and automated inspection drones that keep hardware moving and downtime minimal. Any weak link, such as a slow fuel fill, a cracked flame trench, or a bottleneck in transport, can halt the interoperation. In the era of reusable rockets, the true race isn't just to build bigger engines, but to engineer the ground systems that can keep pace with them. The ability to launch again and again, safely and quickly, now rests on how well these 5 subsystems work together. Starbase stands as a testament to how private capital can reshape the very idea of a launch site. What began as a remote coastal patch in Texas has exploded into an industrial powerhouse covering 150 hectares, engineered for a pace and scale unmatched by any government facility. The heart of this transformation is the orbital launch mount, a steel lattice structure rising nearly 30 meters, designed to anchor the full 120-meter Starship stack as 33 Raptor engines ignite below. Each launch unleashes more than 400 million newtons of thrust, demanding a foundation that can absorb shock and vibration on a level once reserved for military bunkers. After the first integrated flight test in 2023 ripped apart the original concrete pad, SpaceX engineers installed a steel plate flame diverter, a massive water-cooled trench lined with interlocking panels. This innovation channels exhaust hotter than 3,000 degrees Celsius while surviving acoustic blasts above 140 decibels. The deluge system alone can pump over 400,000 gallons of water per launch, vaporizing most of it in seconds to protect pad and rocket alike. Behind the scenes, a $2.5 billion investment fuels on-site liquid oxygen and methane production, eliminating the need for endless tanker convoys. Automated inspection drones, heavy lift cranes, and a dedicated rail spur cut turnaround time to hours, not weeks. Every design choice at Starbase aims for one goal: rapid, industrial-scale reuse. In this new era, the launch pad is no longer a passive slab of concrete. It is the centerpiece of a high-frequency, high-stakes race where infrastructure, not just rockets, will decide who controls the future of space. At Kennedy Space Center, the legacy of Apollo is being re-engineered for a new era of heavy-lift rockets and rapid-fire launches. The bones of LC-39A and LC-39B, once built for Saturn V, are now being reinforced, to handle the stresses of Starship and the Space Launch System. NASA teams and commercial partners are working side by side, retrofitting flame trenches with steel plate liners and expanding cryogenic farms to store hundreds of thousands of gallons of liquid hydrogen and oxygen. The new mobile launcher, too, a rolling tower as tall as a skyscraper, carries Artemis SLS to the pad, while SpaceX prepares its own Starship mount just meters away. This hybrid approach has turned the Cape into a multi-user complex where public investment and private capital have triggered a wave of regional growth. Launch support now accounts for nearly 2,000 new jobs, fueling a housing and tech boom along the Space Coast. Every upgrade, whether it's a new deluge system at LC-39B or a rapid disconnect umbilical for Starship, aims to cut turnaround time and boost launch cadence. The Cape's transformation is a study in adaptation, a government-built foundation, now supercharged by commercial ambition, racing to keep pace with rockets that demand more launches, faster than ever before. At Wenchang Spaceport on Hainan Island, China's planners took a different route, defined by centralized investment and sheer geographic advantage. The site's position at 19 degrees north provides an extra boost for launches to geostationary and lunar orbits, while a deep-water dock allows 200-ton rocket stages to arrive by sea, bypassing the bottlenecks of road or rail. State funding of 15 billion yuan has transformed the area into a fortified complex, buffered by 20 kilometers of protected mangroves. The Long March 9 pad, still under construction, is designed for heavy lift launches and has a projected cadence of 6 to 8 flights per year by the mid-2030s. Environmental safeguards, from turtle nest monitoring to water quality treatment, are written into every expansion phase. Across the globe, Europe's approach is modular and collaborative. At Kourou, in French Guyana, the European Space Agency ELA-4 pad uses a reconfigurable design that can adapt to Ariane 6, Vulcain-derived rockets or future heavy lifters without a full rebuild. Northern launch hubs like S-Range in Sweden and Andoya in Norway are experimenting with pad-sharing models, hydrogen-fueled rockets, and compact water deluge systems scaled down for smaller vehicles. Startups such as Isar Aerospace are pushing for a weekly launch cadence, relying on automated cranes and rapid pad swaps to keep up with demand. The European model spreads cost and risk across nations and companies, aiming for flexibility over brute scale. Together, these sites show that the next era of spaceflight will be shaped as much by the philosophy of the ground as by the rockets themselves. When a rocket as massive as Starship or New Glenn ignites, the launch pad is thrust into a battle against forces that push engineering to the edge. The acoustic shock alone can reach minus 140 decibels at the pad rim, enough to fracture concrete, shear bolts, and loosen steel plates. At Kennedy Space Center's LC-39B, the 2022 Artemis WOI test left behind scorched concrete, exposed rebar, and a cratered flame trench, forcing NASA to halt operations for weeks while crews replaced damaged sections and reinforced the liner with high-temperature steel. Blue Origin's New Glenn pad revealed its own vulnerability in 2023, when a static fire test produced a hairline crack along the trench wall, traced back to thermal gradients that no previous design had anticipated. The scale of these failures is matched only by the speed of the response. Inspection teams now deploy drone-mounted LiDAR and ultrasonic scanners within hours of each launch, mapping every weld and liner for micro-cracks invisible to the naked eye. At Starbase, modular steel plates can be unbolted and swapped in under 48 hours, while NASA's latest protocols call for ultrasonic thickness checks on every flame trench after each SLS flight. Engineers are racing to keep up, But the reality is clear. Every launch is a stress test, and every pad redesign is a lesson written in heat and sound. No matter how advanced the rocket, the pad remains the fragile link, one that must be rebuilt, reimagined, and re-inspected after every blast-off. Sea turtles nest just beyond the perimeter fence at Boca Chica. Each spring, biologists count around 150 nests along the dunes, pausing launches when hatchlings are most vulnerable. Environmental lawsuits have forced continuous monitoring and seasonal launch windows, making clear that even the most advanced spaceport must coexist with fragile wildlife. But the challenges stretch far beyond turtles. Every Starship launch at full cadence would draw nearly 50 million gallons of water a year, enough to fill 75 Olympic pools, most of it vaporized in seconds by the deluge system. Water recycling ponds and closed-loop treatment plants now stand alongside methane tanks, but droughts and local water rights debates keep the pressure on engineers to do more with less. At Wenchang, a 20-kilometer mangrove buffer protects the coast, while desalination plants supply the water needed for each heavy-lift launch. Europe's northern pads, hemmed in by bird migration routes, rely on compact deluge systems and strict seasonal schedules. The constraints are real, but so is the drive to innovate. Concept designers are already sketching ocean-based launch platforms, semi-submersible pads that drift beyond the reach of nesting seasons and population centers. These platforms, inspired by SpaceX's Deimos and Phobos plans, would carry their own cryogenic tanks and water systems, operating under international maritime law. Automation is pushing boundaries too. By 2035, robotic fueling arms and AI-driven inspection could cut pad turnaround to under 3 hours, shrinking the human footprint and minimizing risk to both workers and wildlife. The next generation of mega spaceports will have to balance scale with stewardship, transforming environmental constraints into catalysts for smarter, more sustainable launch infrastructure. The question is no longer just how many rockets can fly, but how wisely the ground beneath them is managed. Right now, the true race isn't just about bigger rockets. It's about building launch complexes that can handle relentless, rapid-fire liftoffs. As nations pour billions into mega spaceports, the bottleneck isn't technology, it's infrastructure. Will reusable rockets truly make spaceflight routine, or will the pad remain the gatekeeper? Let's discuss below.